Ember training, ZigBee architecture. Since ZigBee is a mesh networking technology, it's important to first understand what that means. This slide contrasts a mesh network, such as might be found in a ZigBee deployment, with a star network similar to what you would encounter in an 802.11 or Wi-Fi network or a Bluetooth network. Notice how in the star network all traffic funnels through a central point, like an access point. And while this makes for a very simple routing implementation with low overhead, it makes the central node a bottleneck for traffic and a central point of failure for the reliability of messaging in the network. Devices are limited in their ability to communicate in so much as they're able to talk to the central device, even when the source and the destination devices may be right next to each other physically. By contrast, notice how in the mesh network diagram, each point in the network becomes a relay point for the connection outward to the rest of the network, and one device has potentially several paths to its neighbors. In this kind of ideal mesh network scenario, no one has to be a central point of failure because each node has a redundant selection of links that it can rely on to get the message through the network to its destination. Note that unlike the kind of repeater or range extender access points found in Wi-Fi networks, these intermediate nodes in the ZigBee mesh network can be sources or destinations themselves when it comes to application layer communication, maximizing their effectiveness and reducing the need for unnecessary devices. By leveraging a mesh network topology, ZigBee networks maximize effective communication range. They reduce the cost of the total solution by not requiring specialized repeaters or central access points, and they improve the reliability and robustness of the communications. In this slide, we have a more direct comparison of mesh networks versus star networks, as well as a contrast with the tree topology used by certain variants of ZigBee. Each diagram illustrates how the various nodes of a PAN coordinator, a router-capable or full-function device, FFD, and a few non-routing or reduced-function devices, RFDs, connect to one another in the given topology. Notice how in the mesh topology, all FFDs have the ability to route to those others within range, whereas in both the star and tree topologies, the node's opportunities for routing are limited by how the network was constructed originally. In the star network, all nodes are obligated to route via the PAN coordinator. In the tree network, all nodes must route along the tree links created at network setup time. In all three cases, the PAN coordinator is responsible for initiating the network, but only in the mesh topology is the PAN coordinator not necessarily instrumental to the routing of traffic across the network. If the coordinator is removed or temporarily inaccessible, we can see there are a variety of other paths that messages could take to get around the coordinator to reach the destination. This kind of redundancy and decentralization makes for a much more scalable network architecture with long-term reliability and adaptability. Note that while ZigBee networks can be constrained to a tree or mesh topology, all ZigBee networks have the potential to be mesh networks, provided there are two or more FFDs present in the network. And it's the multi-hop mesh networking capability that distinguishes ZigBee networks from other kinds of wireless topologies. Now let's examine the ZigBee system architecture and see who is responsible for which pieces of the system. At the lowest layers we have the MAC, the medium access control, and PHY, physical layer, which relate to the radio and how it's accessing the airwaves. This behavior is governed by an IEEE standard, 802.15.4, circa 2003, ensuring favorable coexistence with other 802 standard devices, and FCC compliant operation across unlicensed ISM bands within the frequency spectrum. On top of the radio functionality, we have a collection of layers known as the stack feature set. And this is basically the network layer behavior defined by the ZigBee Alliance, detailed in the ZigBee 2007 specification. There are actually two feature sets defined in that specification, ZigBee and ZigBee Pro, but we'll discuss that in more detail in the stack concepts section. Finally, at the highest level, where the application interacts, there's a set of guidelines known as the application profiles, and each of these are defined by a particular working group within the ZigBee Alliance, typically comprised of OEMs, vendors, and other parties who have the expertise or a vested interest in the use case depicted by the profile. Examples include commercial building automation, smart energy, and home automation. Proprietary application profiles are also possible at this layer. So how do these layers translate to the physical design of a ZigBee product? The answer generally depends on who is providing the hardware, the chipset, and who's providing the software, the networking stack. The first variant, often seen in legacy implementations, is the RFIC model, RFIC being a dedicated RF transceiver component as opposed to a microcontroller or microprocessor. In this model, an 802.15.4 compliant RF transceiver manages the PHY and most of the MAC layer, but still relies on an externally connected microcontroller to manage the operation of the MAC and provide the implementation of the ZigBee networking stack itself. Generally, the microcontroller combines the application code with the stack code to produce a monolithic binary that runs on that external microcontroller. However, due to the complexities of porting the stack to different architectures and getting a driver in place to tightly couple the RFIC's operation to what's happening at the stack processor, this model is not considered very portable across various microcontrollers, with stack vendors often limiting their offering in this area to only one or two specific MCUs. The second model of ZigBee design here is the system-on-chip, or SoC design. In the SoC model, all stack layers, as well as the application, are implemented on a single chip, with lower-level stack functions often implemented in hardware as peripherals of the microcontroller. Like the two-chip model discussed previously, the access to stack functionality here is generally provided as library API calls. There may be a certain amount of shared access to peripherals or resources of the microcontroller between the stack and application. While this sharing may place more constraints on the application developer, it ultimately leads to the lowest bill of materials cost among the three models discussed here, and it typically offers the most compact hardware design of the three. The third implementation model, and the newest to emerge in the marketplace, is the Network Co-Processor, or NCP model. In this model, an architecture similar to the SoC allows the stack and low-level radio functionality to all reside on one chip for the best integration and efficiency where stack features are concerned. However, the application interface to the stack, rather than being a library of function calls, is through a serial interface, such as SPI or UART. Using a proprietary serial protocol over one of these interfaces, the host microcontroller can interact with the stack, potentially abstracting these serial transactions into a library or operating system module that better accommodates the needs of the application running on the host. This model allows for great flexibility on the application design and the host processor architecture, and it allows the application designer to ignore many of the implementation details about the stack itself. Depending on the implementation of the NCP firmware may also expose additional features or abstractions of stack behavior that accomplish higher-level application tasks tailored to the kind of application being run. So this would be similar to an ASIC. NCP providers may provide multiple firmware images targeted to different kinds of host architectures, different kinds of serial protocols, or different application profile use cases. For a more detailed examination of these options, including specifics about Ember's platform relative to these areas, refer to the training section entitled Ember Platform Overview and Support Resources. In order to ensure that the stack, the ZigBee networking layer, as well as the MAC and the PHY, has been implemented in a standard way that complies with ZigBee protocol and interoperates well with other stack designs, ZigBee platforms must go through compliance testing at a ZigBee-approved test facility. These test houses are TV and NTS, both of which have previous testing experience with other networking designs and provide global testing facilities for customers worldwide. Application designers wishing to build a ZigBee-compliant product, advertised as such with a ZigBee logo, must have their design based on a ZigBee-compliant stack platform. Recall from earlier in this section that there are two kinds of ZigBee networking stack implementations based on different feature sets, ZigBee and ZigBee Pro. Because the feature sets are different, stack platforms typically are only certified to one of these or the other, and ZigBee Pro certification doesn't necessarily imply ZigBee certification. So, who is the ZigBee Alliance and what do they do? The ZigBee Alliance is a membership organization that oversees the creation and maintenance of software stack specifications, covering network, security, and application support layers. With the help of registered test houses, they also create standards for interoperability and compliance on the aforementioned software stack specifications. In addition to development of standards, the Alliance also has a marketing group that helps to promote use and awareness of the ZigBee brand and technology. There are over 250 member companies in the ZigBee Alliance, including research organizations, stack developers, OEMs and ODMs, contract manufacturers, microcontroller suppliers, and networking tool providers. Managing the Alliance is a 16-member board of director companies known as the promoters. In addition to the promoter level members, there are also two other classes of the ZigBee Alliance members, participants and adopters. While participants, along with the promoters, have the ability to participate in regular conference calls and design meetings and vote on potential changes to the specification, adopter members only have the right to view in-process changes, in-process documents, and implement specifications without being able to influence their development. All levels of ZigBee membership allow a company to undergo compliance testing and logo certification of the ZigBee standard in a commercial product, but non-members are only allowed to view completed specifications. Implementing commercial ZigBee-based products, even if the manufacturer is not seeking end product certification, implies the use of the ZigBee Alliance's intellectual property, so the annual membership fees are intended to serve as royalties toward this licensing. However, organizations wishing to create prototypes, demonstrations, and non-profit implementations of ZigBee can do so prior to obtaining membership. This concludes this section.